Hello everyone, can you all hear me? Okay, great, thank you very much. I wish all of you already had a wonderful Chinese New Year holiday. So after 1 week, I hope you are all refreshed and continue our ENGG 1310 lesson. All right, let me turn on the recording. All right, so the recording is already enabled. So let me see. So last week we stopped. Hold on. Let me mute all of you. All right, sorry about that. For the best effect, and I have to mute all of you to reduce the noise. Okay, so if I remember correctly, last time we stopped on page 57. Let me share my screen with all of you. Share screen. Top 2. Okay. So at the end of our last lesson, we talked about Ampere's law. So Ampere's law can be used to find the magnetic field, which is similar to Gauss's law in finding the electric field distribution. So by using Ampere's law, you can find the magnetic field, especially in a symmetrically distributed scenario with considerably less effort. Okay, so we didn't see examples in our last lesson. So here we move on to slide number 58 so that we can appreciate the usefulness of Ampere's law. So on page 58, we are looking at the problem of a magnetic field outside a long straight wire carrying current. So as shown in this figure, there is a long straight wire that carries a current I directed out of the page. Okay. So in this case, we want to find the magnetic field that is outside this long straight wire. Then we can draw a circle that is outside the long straight wire, with the center located at the center of the wire. So basically, this is the circle that we draw. So that's also the Ampere loop. So in this case, as we can tell, the direction of the Ampere loop is counterclockwise. So by using the right-hand rule, you can tell that this agrees with the direction of the current. Okay, so by using the Ampere's law, we can write this formula on the right-hand side. So the closed loop integral of B dot ds. So in this case, you can tell that B is constant along this Ampere loop. So B, you can take B outside the integral. And then the closed loop of ds, this is simply the circumference of this loop. So it's simply 2 pi r, no problem. On the right-hand side, this is mu naught times I. Mu naught is permeability constant, and I is current. Okay. So this is quite simple. You can get E equal to mu naught times I divided by 2 pi r. So this is expression for the magnetic field outside the straight wire. Correct? No problem? Okay. Actually, if you look back, this expression is exactly the same as what we derived previously on this page. So in this case, we consider the wire is infinitely thin, no thickness. The wire has no thickness. So the R is the distance from the wire to the field point. But in this case, on page 58, remember this R is from the center of the wire to the field location. It's small r. So this r is not from the surface of the wire, it's from the center of the wire because this wire has a certain thickness. Okay, any question? No? Alright, I'm going to move on to the next scenario. So on page 59, we're going to find the magnetic field inside the long straight wire, current current. So this current configuration is similar to the one in the previous slide, but if we want to find the magnetic field inside this long straight wire, then we need to draw an ampere loop located inside the wire. So as shown here, again, the direction of ampere loop is counterclockwise. So you can basically use your right hand to find out the direction of the ampere loop agrees with the direction of current, because the current is pointing out of the page, and the direction of ampere loop is counterclockwise. So they agree with the right hand rule. All right. Again, we can write the Ampere's law on the right hand side, no problem. Still, because of the circular symmetry, B is again the same along this ampere loop. So we can take B out. So eventually, this integral is reduced to B times 2 pi r. All right. On the right hand side, remember for Ampere's law, remember this I is enclosed current. Enclosed by what? Enclosed by the ampere loop. So in this case, because this ampere loop is inside this wire, this I is not equal to I anymore, but only a fraction of that. Only a fraction of that. And because this I is uniformly distributed inside the wire, so basically the I enclosed is proportional to the area enclosed by the ampere loop. So that fraction is pi small r squared divided by pi big R squared. Okay, no problem, right? All right, so by solving this equation, eventually you get this expression, B equal to mu naught times I divided by 2 pi big R squared times small r. Okay, so in this case, you can tell that B is proportional to small r, the radius. But in the previous case, B is inversely proportional to small r. The dependence on the radius is quite different. So basically from these two examples, we can tell that if we draw the relationship between B and R, when R is smaller than big R, that is the radius of the wire, B is proportional to small r. B is proportional to small r. Once small r is equal to big R, this point is based on the surface of the Y. And then after that, when small r is bigger than the big R, then it follows as inverse relationship. Right? So this part R is smaller than big R. This R bigger than big R. Okay? No problem. All right. There's no question. We'll move on to the next slide. All right. So in the third example, you are asked to find the field inside the long cylinder of current by using Ampere's law. Okay, so the difference of this example from the previous two examples is that this wire is hollow. It's hollow. The current only flows in this ring-shaped area. And also, the current is not uniformly distributed anymore, but by following J equal to C times R squared. So you can tell that this is the current density, this J is current density. Just for information, what is current density? Current density is I over A. A is the area. If the current density is not uniform, then you can choose dI over dA if the current is not uniform. All right. So J is the area density of current. In this case, you can tell that because J is proportional to R squared, so J is not uniform. J is not constant. So that means the larger radius, then the higher current density. So that means most of current are flowing close to the surface of this cylinder, right? Most of current flows along the surface of the cylinder. Okay. So here we can still use the Ampere's law because this current distribution is still circularly symmetric, right? It still has the circular symmetry. So we can simply use Ampere's law to find out the magnetic field. All right. So basically, this is how we do this calculation. We want to find the magnetic field at the dot at the radius r. Then we put a concentric Ampere loop through the dot, through this dot. So this is Ampere loop. So at this moment, you can define the direction of the Ampere loop, either clockwise or counterclockwise, doesn't matter. So in this case, we defined it clockwise. But I need to remind you that in this problem, this current is flowing out of the page. Current is flowing out of the page. Therefore, for this given direction of this Ampere loop, this current is considered negative. Because this current flowing out of the page, but this Ampere loop is defined clockwise. By using the right-hand rule, you find that there's a minus sign for the direction of the current. Okay, so next we need to find the current in the area enclosed by the loop. So basically, that's the dark blue region. we need to find out the I enclosed here. So in this case, since the current is not uniformly distributed, so we cannot simply just use the J times the area of the ring. No. Times J times the area of the ring. No. Because in this case, J is not constant. We have to do integral to find out the value. So how we approach this problem? We can start with a ring that is so thin that we can approximate current density as being uniform within it. So basically, we're talking about this thin ring. If the ring is so thin that its current density is uniform, right? Because this current only depends on the radius, not on the azimuthal angle, only on radius. So if the radius is given, then the current density should be uniform along that ring. Okay, so if the area of that thin ring is simply dr times 2 pi r, right? dr times 2 pi r. Okay. On the other hand, the current within the ring is J times dA. Just remember here the J is not constant. So J is a function of R. dA is equal to dr times 2 pi r. Right, no problem. So next, our job is to sum the currents in all the rings from this smallest one that is closest to R equal to A to the largest one that's closer to R equal to B. No, not equal to B, but equal to this R, equal to this R. Equal to this R, because we are not because we want to find out the magnetic field inside this loop. So R should be larger than A but smaller than B. We need to sum the currents from the innermost to the outermost, which is close to R, not to B. Okay. So this is what we have in the derivation. J times dA, and dA is the area expressed as 2 pi r times dr, and J is C times R squared. Okay, so C is a constant, 2 pi is constant. You can take them out, and inside the integral is R cubed. And R cubed, after integral, becomes 1/4 of R to the 4th power. Okay, so this is R to the 4th minus A to the 4th divided by 4. Okay, no problem. So once we find out the expression for I enclosed, then we substitute into the Ampere's law. As I mentioned, because we define the direction of Ampere's loop as clockwise, there's a minus sign here. There's a minus sign. Because in this case, the current is considered negative. Okay, so substitute this I enclosed into here. Basically, this is expression for B. And then we substitute all the specific values into this expression. R equal to 0.03 meter. A equal to 0.02 meter. So here this is mu naught, the permeability constant, and this is so eventually we get B equal to 2.0 times 10 to the negative fifth power Tesla. Okay. C is a constant. Don't be confused with the speed of the light. No, this is not speed of light. This is the this is a constant. The proportionality constant in the expression for current density. That constant. 3 times this one. Okay. All right. So because of definition for this the definition of direction of the Ampere loop, we get B equal to minus 2.0 times 10 to the negative fifth power. That's because of minus sign. Then we find out actually this B is pointing counterclockwise along that Ampere loop. Because we define the direction of Ampere loop clockwise. So here, after the calculation, we find it negative. So that means the magnetic field actually is pointing counterclockwise. Okay, so at the end, the magnetic field has a magnitude of 2.0 times 10 to the fifth power Tesla. Okay, any questions? So for this problem, let me say a few words. So probably the complicated part would be at this step. You need to put the expression for the current density into the integral and then do the integration from A to R. So that's the tricky part, because current density is not uniform, it's not constant. So you have to do the integral along the radial direction. Okay. So far so good. Any questions? No. Okay, no question. Then I'm going to move on to next topic: solenoid and toroids. Well, a student asked question on previous slide, and I guess it's better to clarify. So this student asked why clockwise direction is considered minus. So here, if you look at figure B, you are a choice to define the direction of Ampere loop. So in this case, you define clockwise as positive for this Ampere loop. under this definition, then counterclockwise will be minus. The definition of the positive direction of Amperian rule is your choice. You can define either direction, clockwise or counterclockwise, no problem. But once you choose to define the positive direction of Amperian rule, then everything has to go with that. So under this, and in this case, once you define the Amperian rule, the direction of Amperian rule as clockwise, then the counterclockwise will be negative. Actually, that's what you got here. You got B equal to minus 2.0 times 10 to the negative fifth power. So that means actually B is pointing in the counterclockwise direction. Okay? Of course, you can define the direction of Amperian rule as counterclockwise. In that case, I'm sure that eventually you can B equal to positive 2.0 times 10 to the negative fifth power. Okay? Okay. If there's no more question, I'm going to move on to next topic, solenoids and toroids. So actually, these are the two specific configurations of magnetic components that you see very frequently. So what is solenoid? Solenoid is a long, tightly wound helical coil of wire. So here is an assumption. The length of the solenoid is much greater than the diameter. L has to be much larger than D. If this condition is not satisfied, you will not get a simple expression for the magnetic field. That's it. It does not mean that it's not. It does not mean that it does not exist. Of course, it can exist, but under that situation, you cannot get a simple expression for the magnetic field. Okay, so the figure on the right hand side shows the vertical cross section through the central axis of the stretched out solenoid. The solenoid's magnetic field can be regarded as a vector sum of the fields produced by the individual terms or individual windings that make up the solenoid. Okay. So in this case, in this figure, you can still see some magnetic field lines here, but you must keep in mind that this is for a solenoid that has a finite length. If the solenoid has an infinite length, or in other words, its length is much greater than diameter, then you do not have magnetic field lines outside the solenoid. You only have magnetic field inside the solenoid. Okay. So in the next slide, we're going to find out by using the Ampere's law, the magnetic field inside the solenoid. Okay. First, this is still the expression for Ampere's law. E dot ds. Closed integral equal to mu naught times I closed. So in this case, based on this geometry, we draw a rectangular Amperian loop. A, B, C, D, A. Okay, so then this closed integral is composed of 4 parts. The first part from A to B, second B to C, third C to D, and fourth part D to A. As I mentioned, for a non-ideal solenoid, the B outside the solenoid is equal. Let me correct this. B is equal outside. But inside solenoid, B is not equal to 0. Even B is not equal to 0, the direction of B should be aligned to the longitudinal direction of the solenoid. So that means on part 2 and part 4, because B is perpendicular to DS, so on 2 and 4, this should be 0. B to C and D to A. And on part 3, because it's outside the solenoid, so B is equal to 0. C to D. B is equal to 0. So then, this is simplified as this one. The integral from A to B, B dot ds. And this is simply B times H. H is the length of the rectangle. On the other hand, on the right hand side, this I enclosed is equal to I times NH. N is the number of terms, the unit length. So N times H is the total number of terms that is enclosed by this Amperian law. All right? So actually you find out H and H cancel out on the two sides. You get E equal to mu naught times I times N. So that means the magnetic field inside the solenoid depends only on the number of terms, the unit length, and current. Current and number of terms per unit length is independent of area or independent of the radius of solenoid of the loops. Okay? Alright, so basically you need to keep this in mind. B equal to mu naught times I times N. This is expressed by ideal solenoid. Okay, any questions? Okay, no question. I'm going to move on to talk about toroid. Toroid is a hollow solenoid that has been curved until its two ends meet, forming a sort of hollow bracelet, as you can see from this three-dimensional view. If we cut it along that line or along that plane, then look at from the top, this is what we have. This is what we see, as shown on the right hand side. So this is the right figure is the horizontal cross section of the toroid. The interior magnetic field can be found by applying Ampere's law with the Amperian loop shown here. This is the red circle is the Amperian loop. It has a radius of small r. Based on the symmetry of this configuration, you can tell that the magnitude of B should be constant along that Amperian loop, right? The magnitude of B should be constant along the Amperian loop. Okay, so in this case, we write it down. The left-hand side of this Ampere's law is equal to B times 2 pi r. No problem. again, 2 pi r is the circumference of the imperial loop. And on the right hand side, this should be mu and mu naught times I enclosed. And here I enclosed is what? I enclosed is I times big N, because there are n terms. There are n terms that are enclosed by the imperial loop. So you need to add all of them up to give the total enclosed current. Alright, so after some simple mathematical arrangement, you find out the expression for B. B is equal to mu naught times I times big N divided by 2 pi r. Okay, so here you can tell that B is not constant anymore, and that's shown in the solenoid, but inversely proportional to small r. So that means the larger radius, smaller field. Okay? Are there any questions? No question. No more questions, then we can move on to example number 4, which is a quick practice of what we learned in the last topic. A solenoid has a length of 1.23 meters and an inner diameter of 3.55 centimeter, carries a current 5.57 amp. Consists of 5 closed pipe layers, each with 850 turns long length L. What is B at the center? Okay, remember here, this is what? This is a solenoid. And we already derived that the expression of the magnetic field inside the solenoid is B naught N times I. N is the number of turns per unit length. So N is equal to Bn divided by L. Right? So here, the big N is equal to 850. L is 1.23 meters. On top of that, pay attention, it consists of 5 closed packed layers. So this has to be multiplied by 5. Yes, multiplied by 5. Because there are 5 closed packed layers. Okay. So once we figure out that, then the rest are quite straightforward. So mu naught times small n times small I. And I is current. So once you substitute all these numbers into the formula, you finally get B equal to 0.024 Tesla. All right. Anybody has a question on this? No question? All right, since it's already 5:12, and I don't think we have enough time to cover the next topic. So we're going to stop here today. And if you still have questions, please feel free to leave your question in the chat box. Otherwise, you are free to leave Zoom classroom. Thank you very much for your attention. I'll see you on next Tuesday. Okay?
Okay, thank you for your response. Okay, let's start today's tutorial. Yes, I will record the video. Okay, let's start today's tutorial. My name is Jia Yongheng, and here is my email address. If you have any questions about today's tutorial or your homework, please feel free to email me. Okay, today we will talk about the magnetostatics. Now, here is the first example. I will give you 1 minute to have a look about this example. Here, I will give you 1 minute, okay? Okay, this example is quite easy. For when we calculate the magnetic force on a particle charge, we can use this formula here. F equals to Q times V cross product with B. Okay, remember the sequence is V cross product with B. And for the cross product, the magnitude, we can use in this formula. And for the direction, we can use the right hand rule. Okay. And you should remember that the cross product is a vector. So when you are asked to calculate a force or the velocity, you should always remember it's a vector, and then you need to answer the magnitude of the vector, and you also need to answer the direction. Okay, for this magnetic force, we can get the direction using right hand rule. Here. Okay. For this example, here we get this formula, and for I cross product with I equals to 0, and J cross product with J is equals to 0, since the theta between I and I or J and J equals to 0, so the sine theta equal to 0. So we can get this formula here. You should know that here we have a minus sign. It's because the I cross product with J equals to K. But if J cross product with I, it equals to minus K, okay? So just remember the details here. It's quite easy for this example, but you should remember the details. So you always need to consider the direction, okay? And now if we change the charged particle to a proton, it means the Q here equals to positive charge. And then we can get a negative force. It means in the negative K direction, okay? Here you just need to remember I cross with J is not equal to J cross product with I, okay? They are the opposite direction. Here's the second example. Again, give you 1 minute to have a look. Sorry. Okay. Okay, let's look at this example here. First, this is a electron, right? So it's negative charge. And first, the electron is accelerated by this voltage. And we can simply get the velocity here after the acceleration, right? Using the Q times U equals to the here. Just show you in the next page. Okay. Here we can get the velocity after the acceleration first, and after the acceleration, the electron move to a magnetic field and also an electric field here. And let's see the potential difference in these two plates equals to 100 V. Okay, suppose the potential difference here. Suppose the electric field in this direction, and here when the electron move to this place, and it will have a electric force in this direction, right? And now we want to add a magnetic field so that the electron can travel in a straight line. If the electron can travel a straight line in these two plates, then this electron should have another force in the opposite direction, right? It means that the magnetic force should be in the opposite direction with the electric force, and they have the same magnitude, right? So the following calculation is very easy. Here, first we calculate the velocity, and then when the electron can move in a straight line, it should have a total force equals to 0, and then we can get the magnetic field equals to okay. This is the This is the magnitude, and then you should also tell the direction. Okay, this is the vector. Here, after you calculate the magnitude of the magnetic field, you should also tell the direction. Here, actually the calculation is quite easy. First, you get the V, and then you can get the magnetic field. Now let's look at the next example. Here, again, give you 1 minute to have a look. Firstly, this is the metal strip, meaning that in this strip there are many free carriers. And if we move this metal strip in this magnetic field, and the carriers will move since they suffer from the magnetic field, magnetic force. Right? Suppose there is a positive charge here. And if the magnetic strip moving in this direction, and the positive charge will suffer from a magnetic force, I think in this direction, right? And for the charge with negative, for the particle with negative charge, it will move in this direction. So the electron move in this direction, and the holes may move in this direction. And if there are many positive charge, and this side there are many negative charge, there will be a electric field in this direction, right? And again, for this positive charge, it will suffer from two kinds of force. The first one is the magnetic field force in this direction, right? And another one is the electric force in the opposite direction. So when the electric force equals to the magnetic force, the free carriers inside this metal strip will stop move. So that's why the potential difference won't increase increase to infinite. It's just because the free carriers will stop move when the electric force equals to the magnetic force. Now we need to calculate the speed. It's quite easy. Here, we just need to set this net force equals to 0. Then we can calculate the V. Okay. Again, V is a vector. After you calculate the magnitude, you should always tell the direction. Okay, you should tell the for this question. Actually, the direction is told is in the upward, right? It's given, so we can simply get the speed. Okay. Now the fourth question. I will upload the PowerPoint in the Blackboard. And we do not consider the gravity for this case. Okay, now let's look at this question. Firstly, now for the magnetic force on a carrying wire, we can calculate the magnetic force here using this one formula. Here again, you should always remember the sequence. It's L cross product with B. The direction of L is the current direction. Okay. Now let's look at the question here. For the first question, the magnetic force is on the K direction. Okay, means it's point out of the blackboard, right? It's point out of the blackboard. Now for the magnetic force on the line 1 here, this line, it will suffer from a force in this direction. You can calculate the direction using the right-hand rule. It's L cross product with B. B is the direction of B is point out with this blackboard. So the magnetic force is in this direction. Okay. And for the line 2 here, the magnetic force should be this direction. Right. And for the magnitude, we can get the F. For the question A, the theta between L and B equals to 90 degrees, so sin theta equals to 1. So we can easily get F1 and F2 here. And for the total force for this line, we can, get the F1 and F2 directly, but using the vector rule. Okay. Now, if the magnitude in the direction of I, it means the magnetic field in this direction here. Now the magnetic force for this line 1 equals to, here, think the magnetic force for line 1 is the direction is pointing into the blackboard, and for line 2 here is point out of the blackboard. It means the magnetic force for the line 1 and line 2, they are in the opposite direction, and the magnitude are the same. So the total force for this case equals to 0. Okay, but for this line 1 and line 2, there will be a torque, but just the total force equals to 0, but there will be a torque. Okay, now we move to the final example. I can give you 1 minute. Okay, let's first look at the magnetic field caused by the straight line and a circular wire. For the straight wire, we can calculate the magnetic field using this formula. And this one is for a circular wire. And for the direction of this, the magnetic field caused by the circular wire and the straight wire, we can use the right-hand rule. Okay. Now let's again look at the question. First, if the circular section lies in the plane with of the page, okay, it's the case in this picture right now. So first, let's calculate the magnetic field in this point C. Now we can calculate the magnetic field caused by this circular wire and this straight wire separately. Now for the point C here, the magnetic field caused by this straight wire equals to right, and for this case, the direction is, I think, is point out of the page, so it's a point here. Now for the circular wire, again, the direction here for this case is also point out of the page, right? So we can use the formula in this page, and we can calculate B1 and B2, and now they are in the same direction. So we can simply add the B1 and B2. And again, you should tell the direction is point out of the page. And now if the plane, if the circular plane rotated 90 degrees, it means that the circular now is in this direction. Okay. And for this case, the magnetic field caused by this circular wire should be in this direction. And the magnetic field caused by the straight wire is still in this direction. It's point out of the page. So now they are perpendicular to each other. So again, this is B1 and B2. Now they are they are not in the same direction, so you should add them in a vector row. Okay, let's look at the answer here. For the first case, they are in the same direction, all point out the page. So we can simply add B1 and B2. And for the case B, the B1 is perpendicular to B2, so we can get the total magnetic field using this one. And now you should also always tell the direction. Okay. Now I think this is the end of today's tutorial. Okay. Here, finally, there is a supplementary, so you can see a simple video. It's about the inductive charging. Okay, this is the end of today's tutorial. But if you have any questions about the content of today's tutorial, we can discuss together. Okay, you can open your microphone. Okay. If you have no questions, you can leave the room right now. If you have questions, you can open your microphone and discuss with me. Home 2, I don't think I just don't remember. It's not my duty, so I can't tell you the detail date. And for the questions, you don't need to remember the IJK direction, I think. For the question, any question here, in the question paper, they will tell you the direction, right?
Yes,
for
know
example,
the I and J direction.
The I direction is.
Then how can we know the
here.
K direction after we knowing the
I? This is J, and the K is point out to the page. I think every question will give you the direction in the question picture. And
why not pointing
if
into
they
the
are
page?
not given, you can set the XY direction yourself, and you can you can tell the theta in your answer book. Okay.
Why not pointing into the page?
To use the. Sorry, I can't hear you. Okay, please say again.
Why not pointing into the page, the K direction?
For which one? For this.
Just this example, example 5. Yes.
Okay. For the point, for the direction K, you should again use the right hand rule for this coordination. So you can use the X. I don't know how to show you. Do you know the right hand rule? So you put the.
So the thumb is K direction.
Yes.
The thumb.
The IJK meet the requirement of right hand rule. So
then the middle finger. What is the middle finger? I or J?
What is the
middle finger?
Middle finger?
Middle finger.
Middle finger.
中指。
哦。
它是 J 还是 I？
我是这么记的啊，我没有按这个手指来记。我记的话是从你伸出一个手指，你的手先按到 X 的 direction 伸过去，然后握向 Y，然后这时候你大拇指的方向就是 K 的方向。
懂了，谢谢。右手是吧？右手。
对，右手。Okay. Should be 1 + 1.